Okay, let's move on with Module C. Which I will present all kind of reliability analysis and examples. So what are the analysis types? We have several ones. Starting now, what I want to emphasize that in the morning we talked more about on general things, and the Module B was on component level. Right now we are going on system level. System level on a reliability on a system level, and the afternoon later Module D will be maintenance on a system level. So on a system level, on a product level, we have several analyses like FMEA, FMECA, which means failure mode defect and criticality analysis, fault tree analysis, the stability analysis, MTTR, safety, RBD, the mechanical predictions, and which is also all the reliability parameters are supporting the maintenance used by the APM optimizer. So I have here a sample product, which is the same pressure meter that I explained in the morning. So if we go internally to see what it is built up, we see here a sensor which senses the pressure, the air goes in and senses the pressure. It provides an analog signal which goes to analog to digital converter. And the digital signal goes to a microprocessor. Now the microprocessor compare it with the threshold. If it's the pressure is high, it will provide the signal to the red LED to be lighted, and if it's okay, the green light. Now, in order this will be running and operated, we need to provide power supply. And what we could see, that if we provide power supply to the whole circuits, it means if there is a failure in the power supply, the whole product will fail. So we build up some redundancies. So the power supply goes in, and then we have two voltage regulators which provide the voltage, and we have two capacitors as a redundancy. So it's enough one capacitor, and it's a 1 voltage regulator. Now this you can apply this model to any other kind of product, and basically you can see here that if the pressure is less 10 atmospheres, then the green. If it goes up, the red one. If you look on the left side here, you see the project tree. The project tree, we have the data assembly, which built up from 3 components. The sensor plus a resistor plus the chip. Then we have the indicator, which have the 2 LEDs. And we have the microprocessor, which include the power supply and the chip. And there are 2 capacitors in parallel. So you can see here the power supplies are connected in a Markov model. The 2 capacitors are simple parallel. So if we look into that, this is a generic a project tree which describes the various assemblies, hierarchic level. We can see that now in RBD. So this is the chain. So this means every assembly, if it's fail, the product fail. Here you can see the Markov model and the 2 capacitors in parallel. Now this can be used for other systems, also for mechanical systems. If we have some redundancy, for example, you have 2 bearings that holding something, and if one bearing is not working properly, the other still lets the shaft moving. So what are the possible product failure modes and defects? So the first one will be that the pressure is normal, and we get a red is lighted. So the pressure is below the 10 amps, and then the red is lighted. The other one is that the pressure is high, but we get the green LED is lighted. The next one is no one is lighted. And the next one is when the pressure increases, the green turn off, but red doesn't turn on. It's the same as this one. At the end, both are not lighted. And this is vice versa. Now, I have two questions here for you. Which is the most critical failure here? Easy question. Second, right. Because this is a disaster. So it means that the pressure is high. We say that everything is okay, and it can blow up. So we want to avoid this type of error. The second question is, are we missing any failure? Is there additional failure that can happen? Which one? Excuse me? Both? Yeah. So both can be lighted, you mean? Yeah, okay, right. So it's not here. So this is, if we look into the product, sometimes we cannot predict or we cannot know what are all the failure modes of the product. Sometimes yes. But in cases that we cannot, if we do a FIMICA analysis, failure mode, we can find a failure that will cause that the two lamps will be lighted in the same time. So what is the purpose of the RBD? Is to calculate the reliability and safety of redundant systems, which they have different repair types, time-dependent failure rates, failure to operation and states, hidden failures, and inspections. So if we take this power supply here, and we represent it as a Markov model, so this state say that the two power supplies are working together, each one providing half a current. If one power supply fails, we move to this state. So the second takes the whole power, but we need to do a maintenance action to repair the faulty power supply. If we repair it, we go back. So this is also for the other power supply. Now, if we have the first power supply failed, and we wait long enough, then happen the second power supply to fail, then we have a system failure. Now, what do we think that the failure rates of state 0 is equal to the failure rate of state 1? I will ask again. We have a power supply that works here, half the current. The temperature is lower. Here, it means here two power supplies are working the same. Half current, the temperature is low. Here, we have one power supply fail. The other provide full current, the temperature is higher. Now, the question is, the failure rates are the same in two cases? MTBF, it's mean, is it the same? No, it's not the same. Because if here the stress is 50%, here the stress is 100%. So this means that the assembly is more hotter, it provides you more failure rate. So this is what we mean by Markov analysis, that you have states, and every state have a different failure rate. If it will be the same failure rate, we don't need to do Markov, we can just do a parallel model, a simple model. So Markov is used when a component moves to another state. let's say we can convert it to a mechanical component like a bearing, which have, let's say, 16 balls inside. But if one ball is not okay, it's still okay. The second is still okay. But the failure rate starts to increase because it's about to noise, maybe it's a little bit loose. So we can develop a Markov model for a bearing saying the first ball failed, the second ball failed, and so on. And the failure rate started to increase up to, for example, if we have the 16 balls, if 8 are failed, so we can say that the bearing is failed. So how do we calculate the failure rate of such a bearing with such a situation? Only using Markov model. So Markov model is used when the failure rate is not fixed. It is changed. It has different state. Every state has its own failure rate, which need to be predicted based on the condition and the state. So here at the system level, after we put all the numbers, the failure rates, the TBF, and the time to repair, in this case we took 60 minutes. It's been the power supply, we replace it with a new power supply, the faulty power supply with a new power supply in 60 minutes, which is quickly. So this is why we get here reliability 2 nines and availability about 5 nines, which is very high. Now I will go to describe the models. So a blue one in the model, like this, is a leaf. It means that you cannot divide it into lower levels. It's the lowest level. This is a leaf or a component or assembly that you are not divided it into lower level components. So this is a basic event which cannot be disassembled into components. It uses the failure rate and the MTTR for that. A serial model, 2 elements in serial. If one fail, the system fail. A parallel, that we have 2 assemblies are working. One assembly is enough. If this fails, it's still okay. But in this case, the failure rate is the same. So you can see that we can use a parallel model. It is when the failure rate in the Markov model are the same, simplify the model to a parallel. But when the failure rate is changed with the state, so we need to use the Markov. Then we have a K out of N model. So all the elements are the same. So we can say we have 10 elements. So if you remember the 16 balls in the bearing, we can say, okay, if 8 out of 16 is a failure. So the first fail, it's okay. The second fail is okay. The third fail is okay. So, but in this case, we can use this model only if the failure rate remains the same. If the failure rate does not remain the same, we need to switch back to Markov. We have a standby model. This means that one assembly is running, the other assembly is not working. In all other, the previous models, the redundant one, the other one is working. So all of them are working. In this case, the redundant or the backup is not working, is not powered on. Only when there is a failure, there is a switch that you transfer to it, and then you can use the other component. For example, if you have an aircraft, if you have electronic circuits that fly-by-wire, for example, that helps you to move the wings, and if there is a failure, so you have a redundant system, which is the mechanical one. The mechanical one is not working. Only if you have a failure in the fly-by-wire, the pilot can switch it to manually move the wings So we can use in this case the standby. So we have a system with another system. One can be electronic, the other one can be mechanical, and you switched from one to another. This is a standby. You need to remember that this assembly is not working. So I have a question for you now. Does products which are not operating or not working, do they have some failure rates? So this means that if you have a system which is not operating, just sitting and waiting, if it's collect failure rate or the failure rate is 0. It's been always when you try to use this assembly, which is a standby and not used or not operated, you are always getting it okay. Is it correct what I'm saying? I will ask it again, maybe. You have, let's say, a product, electronic or mechanical product. You put it on the side. Now it's not working. You take it and you connect it to power, or it's mechanical, you try to move it. It's always start to work, or can be you try it and it's not working. You are ashamed, or what? Okay. Yeah, so components, products, they collect failures when they not working, because we have humidity. The humidity goes in and make corrosion. The corrosion, when you start to try to use the product, the corrosion make a failure. But because the product is not working, you don't know. So when you try it, then it fails. So this means that products, components, they fail even you are not using them. So as a recommendation, always electronic parts, it's better to operate. If you have something like that, which is switched off, try this model, because this model will operate the components. It may be in a lower stress, in a lower temperature, but the internal heating of the components will prevent the humidity to go in and to make corrosion. And here I have a story for you. Many years ago, when my kids was small, every summer we took 3 weeks as a holiday. And you know, small kids at home, they use the TV almost 24 hours. All the time, it's on. So this means that the TV is working and eating itself, no failure, because in Israel, the humidity in summer is like here, something like that. So, in this specific year, of course, we switch off the TV. The TV is not working 3 weeks. And we cannot prevent the humidity to go in. So 3 weeks, the TV stay not running. And when we came back, the kids immediately go to the TV and switch it on. And then what a spark, and TV died. Okay, so what I did, since I wanted to know what happened in the TV, I took the TV, opened it, and tried to locate the failure. Why? So I came up to the power supply, and in the power supply there was a big power transistor, and the power supply, and the transistor was isolated from the changes with a special isolator. And what happened? The metal of the transistor developed it was like a needle that goes through the isolation, make a hole, hitting the ground. So the transistor was short to ground. And now we switched on the TV. There was a spark, and everything there was gone. So this shows you that products, they fail even they are not operated. Sometimes it's better to keep them in low fire, we call it, low power, in order it's much better than you switch them off. It's like you have a computer at home. You switch it on and off all the time. If it's, let's say, then less than a few hours, you don't switching them off. But if it's more than a few hours, you switch off. So I recommend you not switching off. Keep them on all the time. Of course, it depends. If the room is air conditioned and you control the temperature, that's better. If you get such a humidity, open space and that, then sometimes it's better to switch it on, off. Okay, anyway, we go now to the other models, a network model. A network model is something that you have several ways of pass. You can see here we need a successful pass from here to here. So we can have this pass, we can have this pass, we can have this pass. So we have several passes. This is called a simple network. So the idea is to calculate the probability of the success passes. So in a traditional RBD, you cannot do that. And here you can see another thing is that this assembly is a bidirectional. So this one goes only this direction, but this one can be going this way or can go this way. So you need to define also what are the passes. And of course, you can do any combination. For example, this is a k out of n. This is a parallel. And those three, this and this one, is connected as parallel also. And this is a k out of n, 8 out of 16, which every assembly is different. If you remember, I told you about k out of n, which the assemblies are the same failure rate. Here, the failure rate is not the same. So if we take a serial model, the failure rate, if it's exponential, we can just sum the failure rate, and we have the failure rate of the product. If we have many, we just sum all the failure rates. And this is example, 2 assemblies. Failure rate is 1 per million hours. The total failure rate are 2. So one failure rate is 1 million hours. So the total MTBF here is 500 hours, if you remember the lamp example in the morning. So this is the resistor example, not the lamp. Now we have 2 in parallel. So this is the MTBF. Now it's more complex formula. It's exponential. If it's only exponential distribution and the repair is cold, the failure rate is again 1 failure rate. So now the MTBF comes of those 2, 1.5 million hours, and this is the failure distribution. And this is the results from the program. So 2 identical assemblies with the same MTBF, take into consideration this exponential distribution. The new MTBF of the combination is 1.5. Now, we have 2 systems like that. In this case, what people are mostly doing, they are calculating one branch this way and calculating the other branch. And now they think it's a serial, we can add the failure rates. But you cannot do that. It's not allowed because now the failure rate is a distribution, and here it was straight line. So you are not allowed to do this type of calculation. So if you take, if you remember, it was in this case, so in this case, 1.5 million. So if we have 2 like this, so it should be half 750. But if we do that correctly, here we see that it's not So the failure rate is this one, and the MTBCF is 916. It's much more than the 750. If we do that this way, this is correct. So we get a higher MTBF if we do the correct calculations. If we have more, the error become bigger and bigger. So the correct calculation here is 582, and the wrong is 373 if we just add the numbers. So remember, if you have a redundant system, never add the failure rates. You need to use a mathematical model which combine the numbers. And of course, if it's a complex model like that, you cannot just add the numbers. You need a statistical model that will calculate it. Okay, till now we dealt with the RBD. Now we go with the FEMIA-FEMICA. So what is this? This is a functional bottom-up analysis from component to top system. We build up component function failure modes in a database. This means we have a component, we need to define what are the failure modes. For example, a resistor, it can be short or open. If it's a mechanical component, let's say like a bearing, one of the failure modes can be that it starts to go heavily, not smoothly, loose. So you need to define what are the failure modes of the component. And you are assigning for every failure mode what is the end effect. And you need to classify the severity of the end effect. If you remember, we go to the pressure meter, the one that the pressure is high and we get a red, green light, this is a disaster. So with the classification, we give it grade 1. So this is a disaster. And what we are looking is for failure modes which have high severity with high criticality in a matrix. So for example, we don't want to have a single component which have a single failure mode which will cause the aircraft to fall. So with high failure rate, with a high severity, we want to detect it during the design, make a change in the design to improve it and to avoid it. Sometimes we cannot, so we put some redundancies. In mechanical components, it means that we need to put some more strengths. We make another component, and we make the metal and the structure there stronger. And the data comes from the FEMICA, serve the basis for safety, testability, and other RAMS analysis. So you can see the sub-block, a block, and a parent block. So this is a model where you have a sub-block, a failure causes, going into the failure modes, going into failure effect. So it goes from bottom to top. So if we take this sensor on this FEMICA, we can see that we have two in the red. So this is high severity with high probability. So in the FEMICA, we want to classify all failure modes, to put them in the matrix, and to see if some components fall in the red area. Red area, high severity with high probability, and we want to avoid them. So we have, for this example, the sensor. The two failure modes of the sensor are here. This is the first one, data less, is severity 1. The data more is severity 2. It's here. So we have those two failure modes here. We have also other 3, 2, and 3 in the yellow area, which maybe we will accept it or not. But what we want that all failure modes will be in the green area. This means a low probability with a low severity. So the idea of the FEMICA is to map all components with their failure modes to see what is the effect of every failure mode on the behavior of the system, to give it a severity and classification, and to put it in the matrix. And we need to deal with those failure modes that are falling here. You can see that as also as a fault tree. So we have end effects, and we see the components contributing. Now we can now inverse it and having those end effects and to see what can cause those end effects. So there is a connection between FEMICA and the fault tree. So the FEMICA is a bottom to top analysis from components to product symptoms, and then we have the symptoms down, what are the causes. This is the fault tree. So this is a different view of the failure propagation. What we also adding in the tools, some kind of to capture knowledge. For example, this is it's a tungsten lamp. Now in a tungsten lamp, special lamp, it was used for an equipment. So what the designer did, he provided the power to the lamp in a ramp signal. So this means that the voltage increase immediately to the maximum and then stay. Now, those kind of components, you are not allowed to provide the maximum. Or let's say a mechanical component, you cannot never turn, for example, the bearing very quickly in the beginning. You need to slow and you bring it up. But the speed that you bring up, the speed of the rate that you change the speed of the bearing can be very fast. So if you do that fast, you can harm the bearing. If you do that slow, it warm up, everything is okay, and you don't get any failure. So there should be some design guidelines when you do a design, and this is coming from the FEMICA. In this case, one of the rules, the design guidelines, is to use a dimmer in such lamps. If I think that mostly it's done in cars today. So the new cars have an automatic dimmer. When you open the door, the lamp is not directly lighted. It takes time and come up, a few seconds even. And sometimes when you close the doors, when you switch off the car, the light goes slowly. So this is to prevent damage to the lamp. But anyway, today in the new cars, they are not using anymore the filament lamps. They are using LED, and LED is a different story. You can switch it on immediately. It's different. So this means that every component, you should know the design limitation, the design guidelines, and when you follow and do a FEMICA, you need also to check those guidelines. In this case was the tungsten lamp. When we did the analysis, we analyzed when it get the power. You get immediately, or you get it in a slow rate. So once we get it, we saw that it's gone in a ramp. We say, okay, the designer, you need to build here a dimmer, automatic dimmer, that the voltage goes slowly, or the speed of running your bearing should be, the rate should be slower. And this is what we, as reliability engineers, can contribute to the design to show them the failures that can happen and how they can improve the design. Okay, testability is the ability of the product to detect and isolate failure. Built-in test or built-in self-test, or it calls the BIST, the built-in test for diagnostic. Mostly it's used for field operators report to or remove remote diagnostic. It depends on the maintenance policy. So sometimes you know from remotely which assembly fail, and you can come up with the exact spare part to replace it, either remotely or locally where you have an indication. the non-detected failure should be detected by external automatic test equipment. So you cannot allow failure will be hidden. We need, once you detect that there are failure modes that the built-in test cannot detect, and this means that you will have a failure and you will not get any alarm that something wrong. For example, this pressure meter, the pressure is high and you get it red. So the built-in test doesn't say anything. So you think it's okay, but up to it will explode. So the built-in test is very important to isolate the failures. In this case, you can see that we have 95% fault detection, and fault isolation is only 63%. So this the percentages are done or calculated from the product failure rate. So 95 of the failure rate is detected. We have an alarm. About 5% there can be a failure, and now we want to see that that failure is not falling in the red area. If it's falling in a green area, okay. But if it's red, it's a disaster. We need to correct our design. So there are several types of built-in tests in a system. When you power on a system, mostly it's done in computers for the memory. You cannot check the memory during operation. An online bit, this means this all the time runs and checks. It can check only voltages and initiate it. It means that someone interfered the system, push a button, and initiate a test. In this case, you cannot do that when you have transmitting antenna. So if you have transmitters, it's very difficult to perform initiate test during operation. You need to do that before. And of course, what you cannot find or detect in the built-in test, you do with external automatic test equipment. So if we take the failure rate of a system as a 100% and we classify what we can do, so we can see that 15% we can detect when we do a power on analysis. Then above that, we can have an online, it's all the time running 75%, and initiated 5. Together, we come up to 95% that we can detect. Sometimes it's good, sometimes it's not. And again, it's depend also if the rest 5% are falling in the red area. If not, it can be accepted. Now, for the isolation, so in this case, we see the failure rate and the 95 fault detection. Now we go to the isolation. Now from the 95%, now we can isolate what is the root cause. One assembly, this assembly, or that assembly, or we don't know which assembly. So this is very important that the isolation will be exactly to the cause. If you don't know that two assemblies can contribute the same error, you need to make a change in the design, or if it fits the requirements. For example, you have a system which has 3 alarms. If this component fails, it makes the 2 alarms. If this component fails, it makes this alarm. So this alarm can be caused by those 2. So if this alarm come up, I don't know which one. But if this alarm is not working, so I can know that this alarm. So I need to build up above another decision maker that will decide. In this case, I have an alarm that anyone can cause this alarm. So if I have the lamp number 3 lighted, I don't know from which is coming. So now I need to another procedure to go into isolate which assembly I need to replace. So here we have a good example. We have 3 assemblies, A, B, and C. Bit 1, test A and C. Bit B, test B and C. You can see here, bit 1, detect A and C. And bit 2, detect C and B. So if we have a failure, the bit 1 fails, it can be either this one or this one, right? But if the other one is not lighted, we know that it's only this one. So if bit 1 is okay, bit 2 is not okay, so we know the disassembly or disassembly. So as a summary, if A fails, bit 1 red, bit 2 is green. So isolation to 1. If B fails, bit 1 is okay, bit 2 is red, come up. So again, the isolation is 1. So if C fails, bit 1 and 2 fail. So, but in this case, if we have 2, I need another decision maker that tells me if bit 1 and bit 2 fails, this is C. So I need to improve my model of the testability. What I have seen mostly by engineers, that every bit can detect all assemblies. This means that I can never isolate to the source code, to the source failure. So the ideal is that every test will all test only one assembly, not 2. So in this case, if I have 3 tests that test A, B, and C separately, the best one. I don't need to make any decision because I know exactly which one was failed. So this is the built-in test analysis. Now the idea is that we classify what are the failure modes, and we say, okay, those tests are tested by bit 1, this is by bit 2, and this is by bit 3. So by giving this indication on the component level, I can say, okay, this component is detected by those tests. And automatically, I get the detection and isolation level. So this means that I have a matrix. From one side, I have all the components, and this doesn't matter if it's electronic or mechanical. We have the list of all components with their failure modes. And from the other side, we have all the tests. And we say, okay, this test this component, and so on. The best idea is to classify only one test. But designers, they like to do that every test will test all the components, which is not good. So the idea is to find what those components that we have too much testing, and to reduce the number of tests. Sometimes to improve the system, we need to reduce the test numbers. And of course, we need to define what is the replaceable assembly on that level. So this is a rule. What is the replaceable unit? If we replace it, the whole assembly, or we replace the component. So you can see in this case that we are replacing the LEDs in the field. No reason to replace the whole assembly. If we can just take out the lamp, it's easy. And those other components, in this case, this is the model. And we are calculating, and you see the fault isolation, which is very poor here. It's about 97%. Okay, what is the summary? We need to define the type of the bit, the test of each bit, the failure detection percentages, failure isolation percentages, those two we get as a result of the calculation. Define the replaceable units in the field, and create a link between failures and tests. This gives us the results. Now we have the fault tree analysis. In this case, I have here an example which a premature detonation. It's a mechanical product, and which this means that we have a few steps that you have some kind of a piston and some kind of a screw and a spring. And when you start it, it starts to move and create, and you have to have steps. If something fails, it's stuck and prevented from a premature detonation. So this means you have here, this failure can occur only if this one happened, this one happened, those two. So if the piston is active and the detonator gives the pulse during 150 milliseconds. Okay, so if those two failures occur in the same time or one after that, this will happen. Now, in order the piston will be active, there can be other three failures. So there will be this, this, and this. And means all those three failures need to occur together. So it's the lock off broken during shooting, piston ready, and spring is broken before during shooting. So you have some mechanical failures that at the end, the piston is active. Now this is not enough. This failure should also be happened. And what will create this failure? This will happen if those two failures will occur in the same time. So switch 1 becomes short during the time, or the switch is invalid until the time. So this failure can be also only if this failure is not occurred. So we can use also not gate. So this is a complex hierarchy of failures and combinations of failures. And at the end, we have a probability of 2.7 and the minus of 48% that this will happen. So we can say, okay, this is a very low probability, and we can be happy because the product is safe in this case. And you can see that how it's built up from the traditional fault tree. This is the end of those two failures. What you can see that the traditional way to present failures takes more room than this one. In this presentation, we see all the parameters easily. We can describe a lot of parameters. This way here, not many parameters you can describe because no room. If you want to put all the numbers, you need to have a big, and you have a lot of holes in the middle that present it. Okay, so we have here what we see in the fault tree. We have an end cause. This means this really a failure mode of a component that happened, and it cannot be created from another component. And this can be one of the gates, a K-autofen, or, and so on, that it's a combination of the failures. Now you have also two types of recovery. Recovery, hot recovery. It means you have a failure that you repair it immediately when it happened, and you don't stop the system. And you have a cold recovery when you stop the system and you correct it. So you can also add those three ways of recovery time. If you have a recovery time, you need also to specify the time. So in this case, you can also build up common causes. So one component or one failure mode create different effects. But you want to continue analyze your system on those different effects. You don't want to combine them. So one component is causing two effects, and you want to continue with your tree with the two effects. So we call it common cause. This makes sometimes easier to analyze because you can see the common cause, how it's affect the two effects. If you don't use the common cause techniques, you need to build up two components, but you need to combine those two components will fail in the same time. So it's difficult. So common cause is the way how you build up the model. Okay, so OR gate, it's either this or this one can happen. XOR gate, when only one is independent event, or this or this. End effect, it should be all those together happen to create an end effect. Priority, it means that the first one should happen the first, and this is the second. So this is the order. If this one is created before this, then it stopped. You cannot go on. And end standby, so it means that you have something which is a standby. So you see some similarity with the models between fault trees and RBD, but the idea is the fault tree is a top-down, and RBD is bottom to top. Key out of n, the same, and a NOT gate. Now, what you want to do to know in fault trees, what is the minimal cut set? It means you have a failure. What are the minimum failure modes that create this end effect? It's like a FIMICA and gives you in one list what are the components or the failure modes that create this mode. MTTR. Okay, MTTR is the mean time to repair. So this gives us the time needed, the maintenance time needed to remove and replace every assembly. And at the end, you see the MTTR calculate. For example, to repair this assembly takes me, in average, 6.1 minutes by replacing this assembly, this and this. And the time I have here, this is the time needed. This is the average with the failure rate. So if I have a component with a high failure rate, which is quick, then maybe it will not affect. If I have a component with a high failure rate, which takes a long time to remove and replace, this really will affect the MTTR, and mostly the time will be given from that assembly. So the purpose is to calculate the average and maximal repair time of a system, parts on different maintenance levels. System is presented as a maintenance tree describing the sequence of disassembly and repair. For example, to repair a pressure meter on O level, it's been in the field, we need to remove a failed SIU at, for example, the data card, this one, and replace it with a spare. To repair the failed SIU data on a D level, it's a shop, we need to remove the components, the internal components. So we have levels of maintenance. So we have the field maintenance, we have the shop maintenance. So the field maintenance can remove assemblies. The shop maintenance can remove components. So, so the MT is the failed part isolation, preparation, replacement by a spare, alignment, and checkout time. It's been the whole time needed from the minute it fails until I know that this component failed. I need to replace it. I replace it, and I check that everything is OK. So the entire time needed to restore the failure. The MCT, if you remember, it's the maximum time to repair with a given confidence probability, for example, 90%, assuming long normal repair time distribution. So if we have a long time repair, much more than the for example here, to repair the pressure meter. In average, took us 22 minutes, but the longest time can be 80 minutes. So if I'm not allocating enough time to complete the maintenance, and I need the system, let's say, after 40 minutes, I will find myself 50 times that I will not be able to complete the maintenance. For example, if you have a failure in the aircraft and you have 1 hour to repair it, otherwise you have a delay and you are not allocating enough time to repair it. So some cases you will not be able to prepare the aircraft for flying. So maybe the air carrier will pay a penalty for that. So this is very important that we know from the beginning how much time we need to allocate for the maintenance, but in average too, it will take us much less, like about 20 minutes. For example, here can be a chair in an aircraft that you need to replace it somehow. It's broken, and they can, of course, fly with a broken chair. They don't sell the ticket. But if they have several chairs and more and more chairs are broken in the aircraft, and every chair takes an average at 22, but one chair is very complex there. It takes more time because at the end, on the back, I don't know, some places that it's difficult to come to all the screws, and it takes more time, and then you are stuck and you have a delay. Now, in order to make a good MTTR, you can have a library of standard time. For example, standard screw, how much time it takes to open and replace it, Allen screws, captive screws, all those mechanical components. So mostly MTTR is done on the mechanical. You don't repair the electronically. Mostly it's a mechanical part. You need to open screws, doors, to find the faulty assembly, to remove and replace it. If you do the same, you can use it for electronic components. If you use a standard time to replace a resistor or a chip on a PCB, but this is done on the D level, and this is offline. So in the D level, we can have more time than in the field time maintenance. At the end, we get this table as a result, which takes into account the preparation, isolation, checkout, connections, and maybe some connectors that we need, screws that we need. So in total, it takes 24 minutes to remove this data. The indicator 21, and this is also 21, similar time. So the MTTR is calculating by the average of multiplication of the failure rate with the time divided by the sum of all the time. The MCT is much more complex. It's a very complex formula. And for doing that, in order to simplify it, we are using some kind of factors. For example, for confidence level 90%, this is the number. And those three numbers are mostly used in the industry in order to calculate the MCT. At the end, what we get, the maintainability, is a maintenance allocation chart and the MTTR report. Now, we have here safety. Is someone working on safety using the IEC 61508? Someone is familiar with this standard? Okay, I will explain in general what it's doing. The problem in the industry that we have equipments that we even do not put attention to them. Here I see some fire alarms. So they stay there all the time, and but we are looking that they will work when there will be a fire. So what we do, they can stay a year, 2, 3, 5 years, and suddenly when we need it, it's not working. So how we make sure those safety systems will work when we need them? The same is a circuit breaker in your home for power. If a child put his finger in the power, there is a special circuit that switch off the power from the apartment. So the kid will not get harm. But who test this circuit? It's written in the spec at least once a year you should go and test it. There is a special switch that you go and you press it and you see that everything shut down. Now if you don't do that, during time the contacts they become such a way that even you need it, it will not be opened because it's closed, and we call it a short. So the circuit is short. It will supply the current. It will be okay. You will see light. Everything will be okay. But once you will need this safety system, it will not work. So the industry come up with a standard. They call it IC 61508 to help manufacturer to specify or more to analyze and to give grades to the safety level of the product. And they call it SEAL, Safety Level Integrity. So you can see here, just took it as an example for the IC. So you say this is level 1. Level 1 is not, so the best is level 5. So you can see that the safety system here is level 1. So our pressure meter is not safe to use because there are not enough redundancy. There are not enough test that is done because the pressure meter can stay all the time and gives you green. That's okay. But suddenly the pressure goes up and they continue giving you green. That's a disaster. So you want to build in something in the equipment that if there will be a failure and the effect is everything is okay, but it should be to give you the alarm. So this product should provide self-instruction or the built-in test or redundant if it's failed, another part start. So totally this pressure meter is not it's not safe because we have here number 1. But if you go down, we can see the highest level we can get here is 4. Why it's 4? Because this is redundant. When we have redundancy, when something fails and the other works, the safety level increases. So only to give you understanding what happened with those fire alarms, there should be a procedure from the building maintenance that they should come once a year with a special utility with smoke that it put it, and they should work to see that it's working. And if it's some of this are not working, they need to replace it. And of course, the electronic system behind this one can be checked. The only component that cannot be checked is the sensor at the end. All other electronic can be checked, and this is done according to the IC 508 to give you the safety integrity level. There are another for automotive also. I will skip it. Okay, so we end up, this as backup slides, which we're not going through that. It's 100 slides. It's too much to go. Let's do a break and continue after that with the Module D, with the maintenance, system level maintenance.